day 19 and 20 I kind of combined into 2 days um, for a variety of reasons. But so this is going to be a little bit longer of a lecture. But it's all about latent heat diffusion and vaporization. And so it's a little bit different what we're doing now. Before we have learned that Q is equal to mc delta T, which kind of, if we know our thermal energy, then we can figure out our change in temperature given a specific heat and mass. Or we've also known that Q or E is equal to K delta T. Yes, I reverted to Q. I probably should stay with E, and I even said I was going to. But either way works, however you want to do it. So either you could use your specific heat or your heat capacity, and that way we know how much the temperature changes. Well, the problem is this only works when you have a liquid, solid, and a gas that stays as a liquid, solid, or a gas. So what happens is at a certain point it's going to change phases. So if I make like a little graph and make this time and then we'll make this temperature, basically let's say if this is for water, you would start off at a certain temperature, blah 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 blah, and this would be as ice. And at a certain point, it would go through a phase change. And during that phase change, latent means without a change in temperature. And so this is where it's going to change from ice to a liquid. And this, of course, occurs at 0 degrees Celsius. Then once you got all of it over to a liquid, it's going to heat up again until it goes through another phase change. That's a really bad line. Ooh, I could use my cool trick I learned. Ha! Watch this. Bam! I'm so proud of myself. Okay, and so this was going to be your 100-degree mark, and this was where it's going to go from a liquid to a gas. And so each of these are phase changes. This is phase change 1, this is phase change 2. But during the phase changes, the substance does not change temperature until all of it is flipped over, and then it can heat up again as a different substance, whether it's solid, liquid, or gas. So, the definition of latent heat diffusion is specifically the amount of heat needed to melt 1 kilogram of a substance, or you could freeze it that way. Vaporization is very similar. That's the amount of heat needed to evaporate 1 kilogram of the substance or condense it. And so the two equations you get are E equals MLF and E equals MLV. LF is your heat of fusion, LV is your heat of vaporization. You will discover that LF, that's your heat of fusion for water, is going to be 334 joules per gram, and your latent heat of vaporization, I believe, is 2256 joules per gram. And so every substance has a different latent heat. It's a characteristic property, and I'll do a couple of example problems that have different latent heats. As stated before, when converting from one state to another, the temperature will remain constant. That is key. You have to think of it as it's going through an entire phase change, and that everything has to change over until you can proceed with a temperature change. And so I will do an example problem later on that kind of illustrates that. So let's take, well, alright, so I'll show you a short 5-second film that kind of inspired this. 5-second films, I don't think they're doing them anymore, but they literally do something in 5 seconds and they try to make it funny. I don't know. But this is kind of where I got the idea from, and I figured it's only going to take 5 seconds, so why not? Okay, so, yeah, some of them are a little bit tongue-in-cheek, things like that. But, yeah, so that's your snowball. Basically, snowball is ice, okay? So, let's say you have a snowball and it's at 0 degrees Celsius. This 0 is key. That's because that's at its melting point. If it said, well, let me do the problem first and I'll come back to what I'm trying to get at. Melting point. 100 grams of water, which is initially 7 degrees Celsius. The final temperature of the mixture immediately after the snow melts is 3. What is the mass of the snow? Okay, So we know that delta, it's a bad delta, delta E equals mc delta T. And then from today, we know that E is equal to mLF. All right, so what do I know? So I know that when let's say I have a little snowball, here's my snowball, and then I have a cup. Here's my cup. Oh, it's a beautiful cup. Yes, it is. When we drop that snowball into the cup, a few things is going to happen. The temperature of the water is going to go down while your snow is going to melt. So two things happen. Now, if it's a perfect insulator, let's say we do this inside of a thermos, I know that all of the energy that goes to cooling down the water is going to go to melting the ice, i.e. snowball. And so what I can do is set these equations equal to each other. So I will say M1C delta T is equal to M2 LF. Why are the two different M's? Because this M right here is for the water, and this M right here is for the snow. We're trying to figure out the mass of the snow, so that means I could say M1C delta T over LF. And plugging in what I know, well, I know that my water is 100 grams. Specific heat of water was 4.18 joules per gram degree Celsius. And the change in temperature, it says it goes from 7 to 3. I'm just looking for absolute values here, so I'll just put it in a 4. Yeah, it does have a negative to it. If I did do the negative, then I would need to put a negative here, because basically any time you're going through a phase change where you're increasing in entropy, then it's a negative value. It's up to you if you want to do that or not. I generally just stick to absolute values and kind of just logically think through it. But yeah, if you wanted to be 100% accurate, you could say this is M1C delta T equals negative M2 LF, because its phase change is going to increase in entropy. But entropy is a little bit beyond the scope of this class. If I'm correct, you cover that in Chem 2. So if you've had Chem 2, bully for you, I suppose. That should make some sense. But if you just want to look at it as absolute values, you could probably totally get away with it like this. That's the way I do it. Anywho. LF is going to be your 334 joules per gram. Alright, so degrees Celsius, joules, that leaves you with grams. That's the only unit. You need it in grams, so everyone's pretty happy. I reach for my trusty calculator to do some calculations. And I get 5. Almost exactly 5, probably because I chose that. Alright, so you get 5 grams of snow. Back to the melting point. I promised you that I would go back to it, and here I am back to it. Okay, so here's why the 0 is important. If, for instance, let's say if, oh, that's bad, I'm on the edge of the sheet. What? Okay, there we go. If, let's say, the initial temperature was, say, negative 10, you would have to account for the energy needed to heat it up to 0. For extra energy. It would make this problem significantly more difficult, but it can be done. You would just need to account for that extra energy to get it up to the melting point. So pay attention to where these temperatures are. That will kind of help you. All right, let's do one that's a little bit more complicated. So let's say we have 500 grams of molten silver at 2827. It's melting point. So here I pointed out that we're not going to have to account for the extra energy. It's dropped into a vat of 5 kilograms of water at 25 degrees Celsius. What is the final temperature of the mixture? The specific heat of silver is around 0.23 joules per gram degree Celsius, and the latent heat of fusion of silver is around 88 joules per gram. Okay, so it's very similar to the last problem in what respect. We will have delta E is equal to M. It's going through a phase change of, looks like, liquid to a solid, so it's LF. And then we have delta E equals MC delta T. So a few things are going to happen. This is a little bit different than the last problem. Let's say I have my block of silver. This is my AG. It's molten and liquid. And it's going to be dropped into this. That's a really bad vat of water. Let's make it color-coded. Hey, look at me go. Yes, that looks like water, doesn't it? Yes, it does. All right, now, when it goes through, it's going to undergo a few things. It's going to drop into the water, and it's going to go through a phase change, which means that the water is going to heat up, right? Because as it changes from a liquid to a solid, the water will heat up. Then you're going to have two different things. You will have a now solid silver and heated water, basically water that has a higher temperature. And then you have to come to a final equilibrium temperature. Well, how does that proceed? Well, let's show you. First, let's find the change of temperature of the water as your silver goes from a liquid to a solid. So I say, okay, MAG for silver, LF equals MH2O C delta T. So I'm looking for the change in temperature here. So I'll take the mass of my silver, 500, times the latent heat of fusion of silver, that's 88. Divide that by the mass of my water, 5,000, quite a bit of water, and its specific heat of 4.18. Okay, so trusty calculator, where did you go? There you are. Okay, so you have 500 times 88 divided by 5,000, then divided by 4.18. And that gives you around 2.1 degrees Celsius. Okay, and notice that your grams cancels out, your joules cancels out, and your grams cancels out, leaving you only with a degree Celsius. So what does this mean? This is this heats up the water. So this heats up water. I'll call it newly heated water. Now, you got to think of it now still as two different substances. You will now have, so we now have AG, that's a solid, at the melting temperature, because remember, it doesn't change temperatures, it's latent, it doesn't change temperatures during a phase change. So that's at 2827 degrees Celsius. And we have water, H2O, now at 2.1 plus 25, that's 27.1. And so we have two different substances. So this is where we use the big TF equation I gave you earlier. And that's the fastest way. So we take M1, I guess we'll call it silver, 500 grams. C, that's 0.23. That's the approximate, by the way. I couldn't find a good number on that. So, and its initial temperature, which is going to be 2827, right? Yeah, we're good. And then M2 is going to be my water, which is 5,000 grams. Its specific heat we know is 4.18 joules per gram degrees Celsius, and its initial temperature, which is not 25. Remember, it's 2.1 higher than that, so it's going to be 27.1 degrees Celsius. Then I'll use my little line that I figured out how to use. Go back. And then over the heat capacity, so that's 500 grams, 0.23 joules per gram degrees Celsius. If you can hear that, there's no one's playing Nintendo. That's just my text messaging. Why people are texting me, I don't know. I don't have friends, so I don't know who's texting me. Anywho, 5,000 grams, 4.18 joules per gram degrees Celsius. So, get my trusty calculator out. Then I go 500 times 0.23 times 2827 plus 5,000 times 4.18 times 27.1, and then I divide those by the heat capacities. That's 500 times 0.23 plus 5,000 times 4.18, close, we get 42.4. So the final temperature, 42.4 degrees Celsius. Okay, so that doesn't seem very high, but you have 5,000 grams of water and only 500 grams of silver. Plus water-specific heat is so much higher. It makes sense. If you've ever watched, like, I don't know, those Smiths, like, dropping molten things into water, the water, it steams up a bit, but it's not going to start boiling or anything crazy like that. Well, it's because we have so much more than that. All right, 15 grams of liquid water is vaporized. So now we have to do a different one, 100 degrees Celsius. So this is the vaporization point, so I don't have to worry about any extra energy. And then, but I do now because it's only going to be heated up as steam to 125 degrees Celsius. So now I do. If the specific heat of steam is around 2 joules per gram degrees Celsius, what is the energy required to heat up the sample? So basically what it's saying is, all right, so we've got water, and it's going to undergo a phase change. And phase changes, it's going to be delta E is equal to mLV. Well, that's to go from a liquid to a gas. Then once it's going to be a gas, we have to heat it up. It's not the phase change, it's just going to be your traditional MC delta T. And that's to go from 100 to 125. And the sum of this is going to be your total energy. And so what we have here is delta E equals mLV plus MC delta T. It's the same substance. So I can pull out my M and just have an LV plus C delta T. And that's what I'm going to do. I take my mass, which is 15 grams liquid. It's LV, remember I said it's 2258 joules per gram, much higher than the latent heat of fusion of water. C is not 4.18. Remember, it's steam now. So it's going to be 2.0 joules per gram degrees Celsius times its change in temperature from 100 to 125 is going to be 25. Celsius cancels. Joules, grams, joules per gram degrees Celsius, joules does not cancel. That was silly of me. Silly! But the grams does over here, by the way. Come back here. 2.0 joules. Alright, here we go. Closing. Now, I'm going to do some calculation. 2258 plus 2 times 25. And then I multiply that by 15, and I get 39,120 joules. Quite a lot of energy. Okay, so quite a lot of energy. The majority of the energy goes into the phase change because you're literally changing its structure, and so that kind of takes a lot of energy. Problem. This is probably one of your most tricky problems you'll have on your homework. You have 4 grams of steam at 100 degrees Celsius, so it's at its phase change temperature. is mixed with 20 grams of ice at 0 degrees Celsius, also at its phase change temperature. What is the final temperature of the mixture? The issue here is you have ice and steam, and both of them, when they come in contact, will immediately undergo a phase change. So your task is to figure out who melts first. The easiest way to do that is to find out the energy it needs to take to change each one over. So I take my 4 grams of steam and I multiply by 2258 joules per gram. And that's going to give me the energy to condense all the steam. That's 9,032 joules. I will do then the same thing, but I will do it for ice to figure out how much energy does it take to convert over all of the ice. And so I take 20 grams, and remember it's 334 joules per gram. And I take 334 times my 20, and I get 6680. What this means is it takes more energy to convert over all of your steam than it does to convert your ice and change it into a liquid. So that means that in this process, all ice will melt. So it's going to take less energy. All ice will melt, and then you're still going to have steam left over. Your job is to figure out that leftover steam. Your job is to figure out, well, how much energy does it take to get rid of the rest of the steam? Well, we'll take the difference. I'll take 9032 minus 6680 joules, and I get 2352. So it's going to take 2,352 more joules of energy to convert the rest of steam. Convert. That's a really bad T. Let's fix that. Oh, there we go. Convert rest of steam. Now, in the process of converting the rest of the steam, you have the ice, which is now liquid water, which is now a liquid, will heat up. So it will heat up as the rest of the steam condenses. Well, how much? Well, I know that you need 2352 joules of energy to convert the rest. So I take my 2352 joules of energy, and then I set that equal to MC delta T. The M being the 20 grams of the ice, which is now water, the 4.18 joules per gram degrees Celsius, and the change in temperature. This will give me how much the ice, which is now a liquid, will heat up in the process of converting the rest of the steam. And so I will figure that out, putting it in my calculator. I get 28.1. So delta T equals 28.1 degrees Celsius. So what does that mean? Okay, so you got to look at two things here. You now have, we'll call it in parentheses, ice, but it's now a liquid. It's a bad L, let's make it a little bit better for now. And that is going to be at 28.1 because it was at 0, now it's at 28.1. Remember, we have to think of our substances as separate, meaning your steam is going to stay all cohesive until all of it's converted over. So that means you now have quote-unquote steam also at a liquid, but it's now at 100 degrees Celsius. And so this is then a traditional TF problem using that big TF equation. So I take my first mass, I guess we'll do ice, well, liquid, water, ice that melted, and I take the 20 grams, and I'll just put a C in here for reasons I'll show you in a second, and its initial temperature, which is 28.1 degrees Celsius, plus the second mass of 2 grams times C again, and then its initial temperature is 100 degrees Celsius. Drawing my little cool line I learned how to draw. And that's going to give me in the bottom 20 grams C plus 2 grams C. Now I told you that it's rare that things cancel, but since I'm dealing with water and water, surprise, surprise, C's will cancel. That's why I just wrote C. I knew this was going to make my life a little bit easier when I input it in the calculator. And so I just take 20 times 28.1 plus 2 times 100, and then I divide that by 22, and I get 34.6. 34.6 degrees Celsius. So, these two substances, both steam and ice, after all of the steam and all of the ice is converted to water, will reach a final equilibrium temperature of 34.6. Like I said, you have one on your homework. I believe it's like the second or even the last problem. One other thing I want to mention is that, for instance, I started off with 20 grams of steam and 20 grams of ice, and I tried to do this problem and realized it doesn't work. Why didn't it work? Because if the amount of energy left over has a temperature change of, say, 100 degrees, well, that means that it's either all going to melt or it's all going to change to steam. So basically, when I had 20 grams of steam, what that meant was that all of the steam would, not all of the steam would condense, all of the ice would melt, and then end up turning into steam. Basically, it's akin to, you get like a glass of hot water, but if you put enough ice into it, eventually it's all going to get down to zero. Basically, one of them is going to dominate. So if you get a really funny number, that just means like your temperature is 112 when you do this little step. That means that it's all going to be converted, and it's all going to be at the one same temperature. So, anywho. Just kind of food for thought. I don't think I gave you one on that. So, all right, that is it.